So we started out with a goal. Remember what our current goal is? Our current goal is to make thousands of hosts communicate with each other. Bridges came to our rescue. Bridges, basically by isolating the collision domains, help interconnect Ethernet LAN segments to form extended LANs. We saw some clever forwarding in this space where we looked at the source address to determine where the hosts are located. The bummer turned out to be these loops in the topology which can cause these frames to loop indefinitely. So in this video we will see how to solve this particular problem. If a graph had loops, how would you get rid of these loops? That's right, by imposing a tree on the graph. So in this particular case, we define the graph in the following way. We consider each bridge and each LAN segment as a node in the graph, and the links in the graph are basically the interfaces that hook them up. Now we are going to impose a tree on this graph. This tree is called a spanning tree because we want this tree to span those nodes that correspond to the LAN segments. Notice that I'm not saying that you should span the bridges, but only the nodes that correspond to the LAN segments. Why like this? Because hosts are connected to the LAN segments which generate data, and our final goal is to find a path for this data to go from one host to the other. This should make things clear. So here is the topology. It is interconnecting multiple LANs via these bridges. Here is the graphical representation of it. As you can see, the LAN segments are represented by these circular nodes and the bridges are represented by these square nodes. And this topology has two loops, one is here and the other is here. So here is one spanning tree imposed on this. In this particular case, I removed this interface as well as this interface to break up these two loops. Now there is more than one spanning tree possible. In this particular case, I have broken up this interface and this interface to break this loop, and I've also removed this interface to break this loop. And in this particular spanning tree, you see that this bridge is disjointed from the remaining tree, but that is okay because, as I mentioned, it is the LAN segments that need to be spanned, which, as you can see, there is a path from each and every LAN segment to every other LAN segment. Now that there are multiple spanning trees possible, the question is which spanning tree to use. An important thing to note here is whatever tree you use, it has to be consistent. In other words, B1 suppose is using this spanning tree and B2 is using the previous spanning tree, then that is not consistent. This can also lead to frames going in loops. Now, how do you ensure that everyone follows the same spanning tree? By ensuring that everyone follows the same set of rules. Before I get into the rules, if I utter the word tree as computer scientists, what comes into your head? I hope it is not fruits. Leaves are okay, but I guess what I was getting at is root. So a tree is typically centered at a root. So here, to determine the spanning tree, we define a root bridge. A root bridge is a bridge with the smallest ID. And for this root bridge, all of its interfaces are activated. Now for every other bridge other than the root bridge, we compute what is the shortest path to the root bridge, and we note this port that is leading to the shortest path to the root bridge, and this port is called the root port. For a LAN segment also, we determine which bridge provides the shortest path to the root, and this bridge is called the designated bridge for that particular LAN segment. And the port connecting the LAN segment to this bridge is called the designated port. It is conceivable that there are more than one path to the root bridge, all at the same distance, in which case the tie is broken with the smaller ID. Here it refers to the next hop bridge. Now that you have determined the root ports and the designated ports, we disable all ports at a bridge that are not a root port or a designated port. By disabling, I mean you don't forward frames on that port, nor do you act on frames received on that particular port. For all practical purposes, it is as good as the port is non-existent. Nothing like an example. So here is a sample topology, and here is the graph that represents this sample topology. Which is the root bridge here? That's right, B1, because it has the smallest ID. First, let's determine what are the root ports for each of the bridges. For bridge 2, which is the root port? That's right, this, because from bridge 2 you can reach the root this way or this way, but this is the smallest path, thereby this is the root port. For bridge 3, this is the root port because this is directly connecting it to bridge 1, which is the root. What about for bridge 4, which is the root port? This one, because there are now two paths, one can go via B2 B1, another can go via B3 B1, but between these two paths, B2 has a smaller ID, so you choose this. Similarly for B5, this is the root port. Now let's look at the designated port. For LAN segments A, B and G, B1 is the designated bridge and thereby these are the designated ports. This is rather obvious. Now let's look at LAN segment F. For F, which is the designated port? Via B2, because this is the shorter path compared to any other part. This part is longer than this, so B2 is the designated bridge and this is the port that interconnects it with B2, thereby this is the designated port. For E, which is the designated port, this, because again for E you could go to B1 via B4 B2 and you could also go via B5 B3, but again between these two B4 is the smaller ID, thereby B4 is the designated bridge and this is the designated port. You could do similar calculation for LAN segment C as well as LAN segment D and you will realize that these are the designated ports. So things are clear so far as to how the root ports and designated ports are selected. Now if you look at bridge 4, this port is neither a root port nor a designated port, thereby this is disabled. Similarly for bridge 5, this is neither a root port nor a designated port, thereby this port is also disabled. Great, the spanning tree protocol seems very simple. As humans, if someone were to give such a topology, we could visualize it like this, apply the rules and determine what ports to disable and what ports to enable. But the bridges don't have such a luxury of getting information on the entire topology. Well, probably not quite. You could potentially use a central node that gathers information about the topology from each of the bridges, apply spanning tree protocol there and communicate this to each of the bridges. What is the problem with this approach? Right? If this central node failed, this entire extended LAN will not work. So we don't want to go for a centralized approach. So the question is, how do we implement this protocol in a distributed fashion? So the spanning tree idea is simple. Now implementation is where you will see the challenge of implementing an idea in practice. So here is the challenge for you. Apply the spanning tree idea by designing a distributed protocol such that a spanning tree is imposed on this extended LAN topology. When I say distributed, I mean that each bridge doesn't have entire topology information. It is going to exchange messages with its neighbors and somehow figure out which ports to keep active, which ports to disable, thereby imposing a spanning tree on this particular topology. So you need to determine what types of messages to exchange, how to send these messages, and how to act when you receive one such message. Like in movies, here is intermission. Take a break, grab a cup of tea, and design the protocol.